Hi, today we're going to be looking at systems of two linear equations in two unknowns, and the term linear indicating there's no power higher than 1 as far as the variables are concerned. And notice that in this typical system of two linear equations in two unknowns, the only variables are x and y. All the other letters that are subscripted are going to be constants. And for example, when we talk about a solution of such a system, that would be an ordered pair of the form xy, which would satisfy both of these equations. So let's look at an actual example with numbers. Here's one. The system composed of 2x plus y equals 4 and x plus 2y equals 5. So if we call the first one equation 1 or E1 and the second one equation 2 or E2, in order to verify that 1, 2 is a solution, we're going to have to substitute 1 for x and 2 for y in both of these equations and see if they become true. So when we take care of that for the first equation, we end up with 2 times 1 plus 2 equals 4, and we're trying to verify that, therefore the question mark. And of course 2 times 1 is 2 plus 2 equals 4, and the last step we go ahead and combine those and we get 4 equals 4. You want to keep the question marks until you actually reach the identity or a contradiction, in which case some mistake must have been made or it's not an actual solution. So we have already verified that one, and we'll do the same thing for the second equation. Again, substitute 1 for x and 2 for y, and we end up with 1 plus 2 times 2 equals 5. Again, the question mark because we're not asserting, we're verifying, and we get 1 plus 4 equals 5. So finally, indeed, we do get 5 equals 5, which is a true statement. Therefore, the ordered pair 1, 2 made both of these equations true, so we call it a solution of the equation. Now, that's great as far as verifying a solution if somebody gives you the solution, but we actually need to know how to find that solution. So we're going to use 3 methods to solve such linear systems. The first method is called graphing. It is the most intuitive method because it actually allows you to see the solutions. The second method is going to be called substitution. And the graphing method is very intuitive but not very efficient. Substitution method is much more efficient. You don't even have to really see the graphs of the two lines to be able to find the solution. But it's only really powerful when it comes to certain types of equations, which we'll discuss. And the final method is perhaps the most powerful method. It's called elimination, also called addition, and that will become clear later why it's also called addition method. So the first method we'll use is graphing. So for that, we basically have these two lines, and I'm just calling the first one L1 and the second one L2. Of course, we have two equations, but as we know, these are linear equations, so once graphed, they will look like straight lines. So we'll go ahead and use this blue table for L1, and we'll use the red table for L2. So notice the easiest way to get those points is just to let x be 0, find out what y is going to be, and let y be 0, find out what x value you'll need. This is called the intercept method because, as we'll see in a minute, when we graph L1 using the points 0, 4 and 2, 0, we notice that those two are actually the points where the line crosses the x-axis and the y-axis. This point here, 2, 0, is called the x-intercept because that's where the line crosses the x-axis. This other one is called the y-intercept because it is where the line crosses the y-axis, and it's actually the ordered pair 0, 4. And for the red chart, we see that when x is 0, we get 2y equals 5, so we just go ahead and divide both sides by 2, we get y equals 5 halves, which is the same as 2 1/2. When y is 0, this term pretty much disappears. We get x equals 5. So right there. So now we're plotting those 2 points, 0, 2.5, and 5, 0. And when we graph them, of course, we're looking for a point that satisfies both equations. And if it satisfies either equation, that means it's going to lie on the graph of that equation. So this is why we said it's so intuitive, because now you can see the solution is right there where they meet. And in fact, if you notice, that does correspond to the x value 1 and y value 2. So the ordered pair 1, 2 is the solution. So if we're going to write that as a solution set, we'll go ahead and write S equals the set containing the point 1, 2, like that. That's a perfectly valid way of solving such systems, but you know, having to graph, etc., is what makes that technique not so efficient. So a much more efficient technique is the substitution technique, which we'll look at now. Let me see if this is going to cooperate with me. All right, so now so for that method, for the substitution method, what we do is we look at the two equations and we want to look for one of the terms which is easy to solve for one of the variables. That means we want to look for a coefficient of either 1 or -1, which works just as well. So we notice we actually have a choice here. We could either solve the first equation for y, or we could solve the second equation for x. And it makes absolutely no difference which one you choose. So let's go ahead and solve the first equation for y. So we're going to get y equals 4 minus 2x. We subtracted 2x from both sides basically, or change sides, change signs, as you know. So now we're going to take this y value, and remember, at the point of intersection, the x and y values are the same for both lines or both equations. So we're going to take that and we're going to substitute it for y in the second equation. So now we get x plus 2 times y, which is, instead of y, we're going to write 4 minus 2x equals 5. So the beautiful thing is that we took a system of two equations in two unknowns, and using a clever substitution, we turned it into a single equation with one unknown, which of course we know how to solve. That's just a simple linear equation. So we get x plus 8 minus 4x equals 5. Combining the terms on the left that are alike, we get negative 3x plus 8 equals 5. So we go ahead and keep the negative 3x and move the 8 over to the other side. So we get 5 minus 8. So we get negative 3x equals negative 3. And if we divide both sides by negative 3, we get x equals 1. Now that we have the value for x, we can take it and plug it into any of these three equations to get the value for y. But of course, the best one would be this one right here, because it's already solved for y. So we take the x equals 1 and this equation, and we end up with y equals 4 minus 2 times 1, which gives us 4 minus 2, which is 2, as we expected, of course. So now we can write our solution set, and when you do that, make sure that you write it in the form of an ordered pair, and you always put the x value first, comma, then the y value, like that. Now, it's extremely important for you to understand that the ordered pair 1, 2, even though it has two numbers in it, is not representative of two solutions. That's actually just one solution. And you can see the one solution in the previous example that we did right there. So this is considered to be one solution. And that's exactly why it's very important that when you type in your solution, that you use these parentheses to let the system know that you're indicating only one solution, which happens to be an ordered pair. So if you don't put the parentheses, the system is not going to like that. For example, if you plug it into something like MyMathLab, it's going to give you an error, and that's precisely because when you don't put the parentheses, the system is going to interpret that as two separate solutions. So you always want to make sure that you use the parentheses when you're dealing with ordered pairs. Now we want to look at the last method we will use for solving such systems. Now, when we want to use this other method, you want to make sure that the systems are written in this form. In other words, the x and y terms on the left side and the number on the other side. If they're not already in that form, then you make sure that they are before you proceed, because we're going to eventually add the two equations, and when we do that, we want to make sure that like terms are lined up. And if you put it in this manner, then notice that they would indeed line up. So the way this method works is we're going to use the fact that if we have an equation, we can multiply both sides of that equation by the same constant and without changing the solutions of the equation. So we notice that I have a 2x here and I have an x here. Or I could focus on the y's and realize I have a y here and two y's. So I can choose whether I want to eliminate the x term or the y term. Then I will multiply one or both of the equations by a particular constant to make that come true. I notice here that if I take the second, so let's say I decide to eliminate the x term. So if I'm going to eventually add the equations and eliminate x, I have a 2x here, so I would want an opposite term here, which is negative 2x. In order to reach that, I'm going to go ahead and multiply the bottom equation by negative 2. And of course, remember, you're going to distribute this negative 2 on the left side and also multiply it on the right side. So you might as well put a negative 2 below each of these terms so you don't forget. So you end up with negative 2x minus 4y equals negative 10. And this one we're not going to be changing, so we're just going to rewrite it. 2x plus y equals 4. Now we have ourselves a new system, but it is going to have the same solution. But this is helpful because now watch. If I add these two equations, because remember, if a equals b and c equals d, one of the properties of equality is that you can go ahead and add the left sides, and that's going to equal to the sum of the right side. So we're using this particular property of equality to accomplish this. And this is why it's also called the addition method. It's called the elimination method because we're about to eliminate x. Notice those two add up to 0, so they cancel out. So all we're going to get is 1y minus 4y, which is negative 3y, equals, now we're going to add these, 4 plus negative 10, that becomes negative 6. Now we go ahead and divide both sides by negative 3, and we end up with y equals 2. All right, so we're not done yet because we only have the y value. So now we can take this, plug it into either of those two equations to get x. And I'm going to go ahead and go with this equation, the second one, because x has a coefficient of 1, which will make it easy to work with. So we have x plus 2 times y, which we now are going to substitute with 2, equals 5. So x plus 4 equals 5. So we get x equals 5 minus 4, or x equals 1. Anytime that time permits, you should go ahead and check your solution, but we have already in the beginning of the lecture, so we know that's the correct solution. So we're going to go ahead and write the solution set again as the ordered pair, containing the ordered pair 1, 2. Remember, always x first, then y. Okay? And that's really all there is to it. So let's go ahead and take a look at another example. Now this one, the equations are 3x equals 2y minus 7 and 6x minus 5y equals negative 16. As long as the x and y have only powers of 1, we know that they are linear equations, and therefore it's okay to go ahead and solve it in the same method that we already looked at. Now, if I use the intercept method again, I end up with, when x is 0 here for in the first equation, I get 0 equals 2y minus 7. So if I solve for y, I'm going to bring the negative 7 over to the other side. I end up with y equals 7/2. It's not a perfect whole number or integer, but that's okay. So of course, notice that's 3.5 as well. You can write it as 3.5. Now, if I make y 0, I get 3x equals negative 7. Just cover that. And you end up with x equals negative 7/3, okay? Which is, of course, negative 2 1/3 when you write it as a mixed number. Now, we're going to do the same with the second line, L2. So when x is 0, we end up with negative 5y equals negative 16. Divide both sides by negative 5. So we get y equals 16/5, which is 3 1/5. And if we go ahead and let y be 0 now, just cover that term, you get x equals negative 16/6, which is the same as negative 8/3 if you reduce it. And if you write it as a mixed number, it's negative 2 2/3. So for the first table, we're going to go 0, 3.5. So 0, 1, 2, 3.5. It's a point around right there. And negative 2 1/3, 0. So negative 2 1/3, 0 will be around there. Then we draw our line right there. Now we're going to repeat with the red table. So we have 0, 3 1/5. So 0, 3 1/5, right around there. And negative 2 2/3, 0. So that's negative 2 2/3, 0. So my picture here is not perfect, so make sure that your drawing is as accurate as it can be, and we should be able to get a good solution by looking at the point of intersection, which looks to be around negative 1, 2. Now I notice here that my placement of negative 2 2/3 was a little bit off, so try to do a better job when you graph it. Okay, so my OCD got a hold of me, and I paused the video and I went ahead and corrected the position of the red graph to better correspond to these points, and you can still see that the solution, which is the green dot, the point of intersection, rides right along about negative 1, 2. So the thing with the method of graphing is that unless your graph is 100% accurate, you can only guess. So we have a good guess at the solution being -1, 2. Now, the nice thing about the other two methods is that we know for certain that the values are accurate. One note I want to make about when you try to do this on MyMathLab, if you try to use the line tool on MyMathLab, you're going to discover that MyMathLab doesn't let you go to fractional points like this. So basically what you're going to do is you're going to plot something close to this. You know, this is like close to 0, 3, and this is close to -2, 0. You're going to plot those, then you're going to click. So as soon as you plot those and you've chosen the line tool, it's going to graph a line going through those 2 points, which of course is not the graph that you want. Then what you're going to do is you're going to click on the first point. You remember you graphed 0, 3. So you're going to click on that, and then you're going to get a pop-up down. You know, if you look carefully on the page, there will be something that will say edit coordinates. So when you see that link come up after you click the point 0, 3, you're going to go ahead and choose edit coordinates. Just click on it, and then it'll open a box where you get to edit those values. So then of course you're going to edit it, and you're going to change it to 0, 3.5. You can even write 3 plus 1 over 2, I believe, and it'll accept that even. So then it'll be exactly the graph that you want. And you'll do the same thing with the other fractional values. I purposely wanted to do this because I wanted to show you how you would handle graphing fractional situations in something like MyMathLab. Okay, now let's try to solve it using the substitution method. As far as the ideal kind of problem for the substitution method, this would not qualify as one, because we usually want to have either a coefficient of 1 or -1, and none of these four variable terms have such a coefficient. But this is still possible to solve by substitution. We just have to prepare it a bit for substitution. And we have to realize the substitution doesn't always have to be just for x or just for y. You can substitute for some multiple of x or y as well. We notice here I have a 3x, and I notice that if I were to just double that equation, in other words, multiply both sides of that equation by 2, I would get a 6x, which I would then be able to solve for and substitute in the second equation. So that's what we're going to do. So we're going to take that first equation and we're going to multiply it by 2. Remember, that means each term has to get multiplied by 2 because of distribution. So we're going to end up with 6x equals 4y minus 14. So now we're going to take this 4y minus 14, we're going to substitute it not for x, but for the entire 6x term. And we end up with 4y minus 14 minus 5y equals -16. So now basically we're going to combine the like terms on the left. We get -y minus 14 equals -16. And if I move -y to the other side, it becomes y. And if I move -16 to the other side, it becomes +16. Basically just adding y to both sides, also adding -16 to both sides. I mean +16 to both sides. So we end up with 2 equals y. Now we're going to take this y value, 2, plug it into either one of these. At this point you have a choice. We'll go with the first equation because it has smaller numbers. It'll make life easier. So we're going to go ahead and get 3x So remember, if we call this equation 1 and this equation 2, we're substituting, we're using y equals 2 in equation 1. So we get 3x equals 2 times 2 minus 7. So we get 3x equals 4 minus 7. So 3x equals negative 3. So we get x equals negative 1. And notice that that agrees with the graphic solution that we previously found. So now we know that that should be the correct solution. And again, if time permits, go ahead and plug it in. It's a good practice anyway. And make sure. So we get solution set contains the order pair. Remember, always put not the one you found first, but the x value first. So negative 1 comma 2. Sometimes students make the mistake of whatever they found first, they plug in first. No, it's always the x value that goes in the first position and the y value that goes in the second position. So there is that problem using the method of substitution. Now, remember what I said earlier, to solve a system using this elimination method, you have to make sure you're in the form which is similar to the second equation. So the first thing we're going to do is we're going to go ahead and put the first equation in that form as well by moving the negative 2, the 2y to the left side, which means change the sign, so you get 3x minus 2y equals negative 7. In other words, subtract 2y from both sides. And the first equation we'll leave alone for now. We just get 6x minus 5y equals negative 16. So far, all we did was we put both of the equations in the proper format. But now we have a choice. We can either choose to eliminate x or eliminate y. Now, if I were to try to eliminate y, I would have to multiply the top equation by 5 and the bottom one by negative 2 so that I get negative 10y and positive 10y. Notice that's just 10 is the least common multiple of 2 and 5, and that's basically what you want to look for. But I realize if I eliminate x, then I would have to just multiply one equation by a given number, for example, negative 2. And that's much easier than having to multiply each of the two equations by some constant. So that's the option we will choose. We'll go ahead and multiply the first equation by negative 2. And that means multiply each of those three terms by negative 2. And we end up with negative 6x plus 4y equals 14. The second equation we're just going to bring over without changing. Like that. Of course, sometimes we don't have this nice option available, and you will have to, for example, eliminate something like the y terms here, and that's no problem. You would just multiply the top equation by negative 5 and the bottom one by negative 2, and everything will work out just as well. In fact, maybe we'll take the time to do that. All right, so notice that if we combine those, these two will cancel out because it becomes 0x, so we just get negative y equals negative 2. Divide both sides or multiply both sides by negative 1, same thing. Multiplying or dividing by negative 1 gives the same result. Now we take that and we go ahead and plug y equals 2 into either equation. Again, we'll go ahead and choose the first equation to work with. So we get 3x equals 2 times 2 minus 7, and we end up with 3x equals 4 minus 7, which is negative 3, so x equals negative 1, just as we found before, negative 1 comma 2. I just want to quickly show you, notice we could have, so we're basically finished with the problem, but I just want to show you an alternative approach. So what I would like you to see now is what happens if we actually eliminated the y term. So I'm going to go ahead and just erase some of this. And now I want to go ahead and show you how you would deal with eliminating something like the y term. So to do so, we would have to multiply the top equation by 5, the bottom one by 2 to get to the nearest common multiple. But notice how they're both negative. So if I want to get opposite signs, I'm going to multiply one of them by a negative number rather than a positive. So I'll just make the first one negative 5. So notice that means we're going to multiply each term in the first equation by negative 5 this time. And we're going to multiply each term in the second equation by 2. So notice we end up with, for the first equation, now we have negative 15x plus, watch the signs, 10y equals 35, and we have 12x minus 10y equals negative 32. So at any point where you feel like you should be able to do something, as always, pause the video and finish it on your own. So we end up with negative 3x equals 3, because the y's cancel out. So we get x equals negative 1. Again, we can go to either one of these equations and get y. So we'll just go to the first one because of the smaller coefficients. So we get 3 times negative 1 equals 2y minus 7. So negative 3 equals 2y minus 7. So we get 2y equals negative 3 plus 7. So 2y equals 4. So y equals 2. Again, we got the same solution. So just so you know, if you did this, let's say you had paused the video and you were doing this on your own, I don't want you to think that that would be incorrect. You have options here. So negative 1, 2. And there is how you approach that. Make sure you pause and you figure out that how to do this on your own before you proceed. Okay, now we want to look at a couple of special cases. Remember that when we were solving just a single linear equation, we sometimes had no solution and we sometimes had infinitely many solutions. And most of the time we only had one solution. So now we want to look at a similar situation with two equations in two unknowns. So taking a look at this first equation on the left, let's say that we want to solve that equation by the elimination method. I can see a typo here. Let me go ahead and correct that in 1 second. Okay, that's better. That wasn't supposed to be 63 here. That was supposed to be 6y. So if we go ahead and try to solve this by elimination, it's very easy to go ahead and multiply the top equation by negative 3. So that's what we'll do. It will go ahead and multiply that equation by negative 3. We end up with, and don't forget to multiply each term by negative 3. So we end up with negative 3x minus 6y equals negative 9. Now, if I go ahead and multiply the second equation by just 1 because it's already 3x and that's all I need, meaning basically don't change the second equation. So 3x plus 6y equals 10. Notice we're ready to eliminate x. We're gonna go ahead and cancel those out, but we notice, oh, there's another cancellation. Those cancel out. So we just have 0 on the left side and we have 1 on the right side. As you know, this is a contradiction. So what does that tell us? That basically tells us that we were trying to do something impossible. We were trying to find the point of intersection of two lines that never meet. And what kind of lines are those? I'll let you think about it for a minute. Okay, I think you realize they would be parallel lines. So when you reach a contradiction like this while trying to solve a system, that means you have one of those situations. So in these cases, you say no, therefore no solution, or you can write S equals the empty set or the null set. Now, on the other extreme, let's look at this system on the right. We notice we can quickly solve this one by multiplying the top equation by 2. And that's what we'll do. So let's go ahead and do that. So let's go ahead and multiply the top equation by 2. So that means each term, because of distribution, needs to be multiplied by 2. So the top equation now becomes 2x plus 4y equals 6. The second equation we just multiply by 1. In other words, leave alone because multiplying by 1 doesn't change anything. So we get -6. Now if we go ahead and combine the equations, notice these cancel out, so do those, but so do those. So we end up with 0 equals 0. Now in this case, that doesn't mean that you have no solution. That means you have actually infinitely many solutions, because if you take a look, you realize that the second equation is just a constant multiple of the first one. Notice when you multiply this equation, for example, by -2, you would get this. Or this is also considered a constant multiple of this. If you multiply both sides of this equation by -1/2, you'll get this equation. In other words, these two equations are basically representing the same line. And that's why their point of intersection, they're going to have infinitely many points of intersection when you look at the graphs. So therefore, the way we represent these solutions, this is an identity. Therefore, we say infinitely many solutions. And it used to be that this is all we required of students. But the problem is, when you ask the student to generate 1 or 2 of those infinitely many solutions, they wouldn't be able to. So now we ask you to continue saying more than that, because it's not, remember, while there are infinitely many solutions, not just any ordered pair in a plane is going to be a solution. They have to satisfy certain conditions. So we'll say of the form. Now we're going to say they would have to be of the form of an ordered pair, but they have to satisfy, well, remember, if they satisfy one of these equations, they'll satisfy the other as well. So you don't need to write both. You can just write one of them. And if you just write this one, that will be sufficient, such that x plus 2y equals 3. So why is writing this important? Because now you can actually generate as many solutions as you want, and it'll be correct solutions. For example, let's say I look at a solution where the x value is 0. then that means 2y equals 3, so y equals 3/2. So there is one solution. Or I can look at a solution where the y value is 0. So I can let this be 0 and I would get x equals 3. So there's another solution. Or I could get picky and say, hey, I want you to make a custom solution for me. I want a solution where the x value is negative 2, for example. Well, no problem. All you have to do is plug in negative 2 for x. So you get negative 2 plus 2y equals 3. And you go ahead and solve for y. So you get 2y equals 5. So y equals 5/2. So there is that custom solution. So anyway, you can see the choices are countless. In fact, there are infinitely many of them. But anyway, these are the two extreme cases. One case in which you have no solution, another in which you have infinitely many solutions. And that brings us to the ability to now classify all systems of linear equations in two unknowns. So make sure you absorb these two before you proceed. Okay, I decided we should look at one more example before we do the full classification, because I wanted you to know how to handle fractional situations. And the problem that you can see has a lot of fractions in it. So the best way to deal with something like this is, because we're dealing with equations, we're gonna clear the fractions. That's the best thing to do at the outset. So we notice that for the first equation, the LCD is just going to be 12. So that's what we're going to do. We're going to multiply the first equation on both sides by 12. And remember, since we distribute, we're going to multiply 12 and distribute. That means each of those two terms, and as well as the one on the right side, needs to get multiplied by 12. So if I just write a 12 over here carefully next to each, I know that I can do some cross canceling. These two will leave me 3. Those two will leave us 2. And these two will just leave us 1. So the new equation that we get after clearing the fractions is going to be 3x minus 2y equals 1. And we'll take care of the second equation now. We notice the LCD is once again 12. So we're going to go ahead, and this may not always be the case, it just happens to be so in this problem. So we're going to multiply again both sides by 12. Okay, those 12s didn't come out too nicely. Let me try one more time. So again, we can cross cancel, and we get 6 over here, we get 4 there, and we get 3 there. So the new equation, which is going to be clear of any fractions, is going to be 6x plus 4y equals 3. So you can see that that's a much simpler equation, system of equations compared to the one with fractions. But the beauty of it, it's going to have the same solutions. Just to get that point across to you, let me give you a really simple example here on the side. Let's say you have x plus 2 equals 5. That's a very simple equation, right? If you solve it, you get x equals 3. We know that, right? Now watch. Multiply both sides of that equation by, say, 4. So you get what? So you get 4x plus 8 equals 20. Remember, we're multiplying it by 4. Now solve this new equation. So you get 4x equals 20 minus 8. So you get 4x equals 12. So you get x equals 3. See, this simple example I showed you on this side is just demonstrating the fact that if you take any equation and multiply both sides of it by a constant such as 4 in this case, right? The beauty of it is you don't change the solution. See, the solutions are the same. That's why this works. It's important to understand that. All right, so that was just a little, side note. Let me go ahead and erase this now so we can get back to our main problem. All right, so now we notice we have a system of two equations in two unknowns. I could either eliminate x or I could eliminate y. In this case, I'm going to choose to eliminate y, even though the number that needs to be multiplied is going to be the same. The beauty is that these are already have opposite signs. So now it'll be much quicker to do so. So we're going to multiply the top equation by 2. And we will leave the second equation alone. So now when we do that, don't forget you need to multiply each of these by 2 because of distribution. So now we end up with 6x minus 4y equals 2. And we have 6x plus 4y equals 3. Now, if we add those equations, we notice that we end up with 12x equals 5. So I get x equals 5 over 12. All right. The nice thing about this problem is that it gives us an opportunity to discuss a new way to get our second variable's value. Notice that at this point, I have the option of taking this 5 over 12 and plugging it in for x, in either of these two equations and get the corresponding y value. However, I may also choose to do the following. I may decide, no, I don't want to deal with plugging in that kind of difficult looking fraction in here and getting an answer. So what I could always do, if I prefer working with whole numbers, is I could take this system that we have here, bring it back down here, write it again. And I could go ahead and eliminate again, but this time I will eliminate x. So I'm going to go ahead and multiply the top equation by -2. So I get -2 multiplied by each of those, and I end up with a new equation, -6x plus 4y equals -2, and the second equation is just 6x plus 4y equals 3. I leave that alone. Now I go ahead and add the equations. These cancel out. I get 8y equals 1. So I get y equals 1/8. And now I can write my solution set as containing the ordered pair 5/12, 1/8. All right. So just so that you know, we're finished, but I just want you to know you could have also taken the 5/12 and plugged it into, say, the first equation or the second. I'll go with the first because it has smaller numbers. And you would have gotten the same thing, just so you can see. So you would have had 3 times 5 over 12 minus 2y equals 1. And that gives us, here, notice the 3 and the 12, They're going to cross cancel, leave us 4. So we end up with 5 over 4 minus 2y equals 1. Now we'll multiply both sides by 4 to clear the fraction. So we end up with 5 minus 8y equals 4. So let's move the negative 8y to the other side, becomes 8y, and bring the 4 over, so it becomes negative 4. So we get 8y equals 1, or y equals 1 over 8, which is of course the same thing we got here. So either method is fine. I did want you to see this because notice the values here kind of worked out nicely, but sometimes the fraction can be quite nasty, like 357 over 769 or something like that. Now, if you get a fraction like that, you'll definitely want to go with this approach rather than plugging it in. But if the fraction is simple enough, like 5/12, and the numbers are cooperative, like notice here, these canceled out, then you could always just plug in to get the value rather than go through and eliminate again. But notice here we eliminated twice. We eliminated y first, we got the x value, then we eliminated x, and we got the y value, and that's always an option. So that basically shows you how to do all these problems and solve them. Now we'll look at the classification. Make sure you absorb that before you proceed. Okay, finally, we want to talk about the classification of these linear systems. Notice that the most common type that you're going to encounter on your homework are going to be the type where two lines intersect at just one point, such as these two lines here, given by these equations for a solution of 1, 2. And this kind of a system is called consistent because we call any system that has at least one solution consistent, and independent as well because the two lines are distinct lines, and that's what we call a system containing two distinct lines. And don't forget, these kinds of systems have one solution. Now, they basically come about if the two equations, linear equations, have different slopes. So the nice thing about the slope-intercept form is that it quickly tells you if two lines have different slopes or not. Let's go ahead and put the first equation in slope-intercept form. So we have 2y equals negative x plus 5. Remember, slope-intercept form, y equals mx plus b. So we get, go ahead and divide both sides by 2. So we get y equals negative 1/2 x plus 5/2. Let's do the same to the second equation. So we get negative 3y equals negative x minus 5. This time we're going to divide both sides by negative 3. So we get y equals positive 1/3 x positive 5/3. So anytime you have a system where the two slopes are different, the two lines are definitely going to meet at only one point. So generally speaking, if you have y equals m1x plus b1 and y equals m2x plus b2, the characteristic of this kind of a system, which is consistent and independent, is that m1 does not equal to m2. There's not a whole lot we can tell you about the b's because, for example, here, notice the y-intercept of one line is here, they're different. One is here, one is here. But these two, this intersection could have happened right here. In other words, you could have had two lines that intersect like that. In this case, the b's would have been the same. So there's not a whole lot we can tell about the b's, but there is something we can say about the slopes. They have to be different for the two lines to meet at only one point. The next kind of system that we get is the one that has no solution, because notice the two lines are parallel, and this parallelism is going to stay there forever, so they're never going to intersect, at least not in a plane. Now, if this were on a sphere or something like that, that's a different story, and we don't get into that in this class. But notice that on a plane, two parallel lines never cross. So therefore, here we would get a system that's inconsistent, because remember, to be consistent, the system has to have at least one solution, and the system is still independent because the two lines are distinct. And if we did the analysis that we did like on the last one, solve the first equation for y and to put it in y equals mx plus b form, we would get negative y equals negative 2x minus 2, divide both sides by negative 1 to get y equals 2x plus 2. If we do the same to the second equation, we would get negative 2y equals negative 4x minus 7, divide both sides by negative 2, and we would end up with y equals 2x plus 7 halves. So what we need to notice here is that we know that parallel lines have the same slope. Notice here we got the same slope, but also notice this is also very important, that the y-intercepts be different, because if the y-intercept, if the slopes are the same, that means the lines are parallel, and the y-intercepts are the same, that means they would be the same line. So the characteristic of this kind of a system is if we call one y equals m1x plus b1, and the second one y equals m2x plus b2, what needs to be happening to get this kind of a system inconsistent and independent is that the slopes have to be the same, and remember, this means both conditions have to be met, and the y-intercepts have to be different. So if you put any system into a slope-intercept form and you discover this, you know immediately you're going to have an inconsistent and independent system. Make sure you understand why. It's never beneficial just to memorize facts, because they won't stick. Memory is not a very reliable friend, remember that. Okay, so finally we want to look at this kind of a system where one line overlaps with the other. There are actually both of these, the graphs of both of these lines are here. It's just that they happen to overlap. So as you can see, the two lines would have infinitely many points of intersection. In fact, any point on either line is going to be a solution of such a system. So now, again, if you put both equations into slope-intercept form, let's go with the first one. We get negative y equals negative 2x minus 2. Go ahead and divide both sides by negative 1 to get y equals 2x plus 2. The second equation, I get negative 3y equals negative 6x minus 6, divide both sides by negative 3 to get y equals 2x plus 2. And that's the beauty of the slope-intercept form. If two equations are really representing the same line, even though they may look different in other forms which are not the slope-intercept form, what I mean is if they look different in any form other than the slope-intercept form, once you put them in a slope-intercept form, all the superficial difference in them goes away, and you can see that the two equations would be identical in slope-intercept form. So we notice that if we have the general equations y equals m1x plus b1 and y equals m2x plus b2, as far as the classification of this kind of a system, which is consistent because it has at least one solution. In fact, it has, as you know, such a system would have infinitely many solutions. you should go ahead and try to solve this using the methods discussed earlier to see that you do indeed end up with an identity. You should also solve the previous one using the methods we discussed to realize you do indeed reach a contradiction. Now, so what we want to specify here is that in order to have this kind of a system, notice that not only do the slopes have to be the same, the y-intercepts would have to be the same too, so that the two lines become identical. So here we have m1 equals m2 and b1 equals b2. And there is the complete characterization and classification of all these systems. So just like with a single linear equation, systems of two linear equations are either going to have one solution, or they're going to have no solution, or they're going to have infinitely many solutions. So this is the case with infinitely many solutions. The previous one we did is the case with no solution. And the first one that we looked at was the one which had only one solution. And that's basically all there is to these systems. You are now masters of systems of linear equations in two unknowns. So take care until the next time that we meet.